We're continuing our discussion of parallel resistors, circuits in which two resistors or more resistors are connected in parallel. We'll focus our attention on the case where there are just two resistors in parallel. That's the more common situation that we encounter in this chapter dealing with electrical circuits. I show a pair of resistors that are connected in parallel, and I show a current coming from elsewhere in the circuit approaching what we will call a branch point. The current will divide generally unequally, some of it going upstairs, some of it going downstairs. We refer to this portion of this pair of parallel resistors as the upper branch, and this is the lower branch. A current I approaches the branch point and exits at this branch point. Whatever current approached this branch point, that's the same as a current that combines to leave the second branch point. The currents are labeled I1 through the resistor R1 and I2 through resistor R2. It's the purpose of this lecture to show you how to calculate the amounts of current in each of the two branches. I'll first show you what the result is and then describe the general rule that you will follow. Consider in this example 20 amperes approaching a branch point, two resistors in parallel, 3 ohms and 7 ohms. We label the current to the top resistor, the upper branch resistance, R1. Current is I1, lower branch, R2 and I2. 20 amperes come in, divide unequally as in general, and combine to give the same current out of the pair as entered the pair. Here's how you calculate the current in the upper branch, I1. It's a fraction times the entering current, 20 amperes. That fraction is shown here as that ratio. It's, if we're looking at the upper branch, the ratio has in the numerator the other branch's resistance. To complete the ratio, we have the sum of the two resistances. That ratio times 20 is 14 amperes. Now we'll calculate the current in the second branch. The current through the lower branch is the other resistance, the upper branch resistance, 3 ohms, divided again by the sum. That's 3/10 of 20 gives you 6 amperes. You need not calculate the lower branch current in this somewhat more complicated manner if you recognize that the sum of the currents in the two branches must equal 20. You have 20 coming in and it divides. We earlier found that the current to the upper branch is 14, but that leaves 6 to be accounted for, and of course the 6 amperes travels through the lower branch. Now I'll write down the two expressions that you can use in cases such as this where you have two resistors and they're in parallel current coming into a branch point. It's what I call the other divided by the sum rule. The other divided by the sum rule. Here it is. The current in the upper branch, I1, is the other resistance, the resistance in the other branch, R2, divided by the sum. That ratio times the incoming current was 20. The same rule works for the lower branch's current. The current in the lower branch is the other branch's resistance divided by the sum. That fraction, that ratio, times the incoming current gives you the needed current. Again, I call this, and no one else does, the other divided by the sum rule. Let's review what we already have said. In this combination of two resistances that are in parallel, 3 ohms upper branch, 7 ohms lower branch, and approaching the branch point is 20 amperes of current that will split. To find the current in the upper branch, we multiply the incoming current by the fraction shown here. That fraction is the other branch's resistance. It's the lower one. 7 divided by the sum of the two resistances, 3 and 7. And we got, as you recall, 14 amperes. Subtract the 14 from the 20, and that leaves just 6 downstairs, which we can confirm using the other divided by the sum rule. That concludes this brief presentation of the method that you can use to determine the amount of currents that go into the two different branches in a pair of parallel resistors.